Good morning or afternoon or evening, whenever you may be watching this lovely video. We will be covering section 2.3 from the Precalculus Enhanced with Graphing Utilities by Sullivan and Sullivan today. And we'll be learning all about properties of functions. So I'll let you read over our goals here. And when you're ready, go ahead and start the warm-up problem. So the warm-up problem is about testing for symmetry. So if you need to look back in your notes, go ahead. Otherwise, pause the movie and warm it up. Okay, let's see how you guys did. So testing for symmetry, starting with the x-axis. Whoops. So remember, for the x-axis, we replace y with negative y and see if we get the same equation. And do you see we will not get the same equation if you isolate the y and by multiplying through by negative 1, you would end up getting positive x squared minus 3, which is not the same. So checking the y-axis. So for the y-axis, what do we do again? Great, we replace x with negative x and see if we get the same equation. So y equals negative x squared plus 3. Y equals negative. When you square that negative x, you get positive x squared. And that is indeed what we started with. So the graph is symmetric. With respect to the y-axis. All right, so here we go. Even functions. A function f is even if for every number x in its domain, the number negative x is also in the domain, and if you evaluate the function at negative x, you get the original function back. So our warm-up problem was an even function because we changed the x's to negative x's and then evaluated, and we found that we got the same y value back, the same function back. So that here, if you see, was an even function. We didn't have it in function notation, but this is a function and it turns out to be an even function. All right, so next up, odd functions. Well, you've got an odd function if for every number x in its domain, the number negative x is also in the domain, and if you evaluate the function at negative x, you get the opposite of the function. So it basically ends up having symmetry about the origin, I believe. Okay. Or maybe not only that, but functions that are odd are also symmetric about the origin. Okay, so here's a theorem. A function is odd if and only if its graph is symmetric. Oh, there you go, symmetric with respect to the origin. And a function is even if and only if its graph is symmetric with respect to the good y-axis. Okay, so here we go. Determine whether each graph is the graph of an even function, an odd function, or a function that is neither even nor odd. So in the first one, I'm looking at this guy, and if I look to fold this graph on the y-axis, do you see we would have symmetry? So this one would be considered to be even, because we just learned that if you have symmetry with respect to the y-axis, you have an even function. Okay, let's look at B. First, let's see if we have symmetry with respect to the y-axis. So when I look at the y-axis here, and if I think about folding, this graph does not have symmetry about the y-axis. So now looking at the origin, if you replace x with negative x and y with negative y, you're not going to get the same graph back out. You can pick really any point. So do you see you've got a point here, which is at approximately, 3.8 or 9, and then you've got it over here at about maybe 65, something like that. So at negative 3.9, negative 65, you don't have another ordered pair, right? You do not have an ordered pair here. So we're going to say, good, neither. And what about this one? In this case, if you look, you see that I see an ordered pair here, which appears to be at about negative 1.5, positive 3. And if I go over here to positive 1.5, negative 3, I have an ordered pair. So approximately negative 1.5, positive 3 is on the graph. Positive 1.5, negative 3 is on the graph. You see how they're swapped? So we would call this one, good, odd. Okay. So now, determining algebraically, you just do the test, but now you're only plugging in x or negative x, and you may have to do a little more work. If it's even, you'll get an answer right off. If it's odd, you'll have to do some more work. So here we go. First of all, let's take a look at evaluating h at negative x to see what we get. We'll need that either way. So this will be 3 times negative x, the quantity cubed, plus 5. So I'm plugging in, wherever I see an x, I'm plugging in a negative x. So h at negative x is equal to 3 times, when I cube that, do you see I'll get negative x cubed? So actually, I'm just going to write this as negative 3x cubed plus 5. Good so far? So, do you see that this is not equal to, so let's kind of go to the side here. H at negative x is not equal to h at x. So h is not even. So now let's get some more information. So this is our first conclusion. So now let's figure out what negative h at x is equal to. So basically you're just multiplying both sides by negative 1. So you're multiplying the whole side by negative 1. So negative h at x is equal to negative 3x cubed minus 5. So negative h at x, actually, we'll do it in order. H at negative x is not equal to negative h at x. That's not the same. So h is not odd. So what we found is our answer for this guy is neither. It doesn't fit either requirement. So this function is neither odd nor even. And we're done. All right. Next up, capital F at x is 2x all divided by absolute value of x. So again, let's just see what we got. Capital F evaluated at negative x will be 2 times negative x divided by the absolute value of negative x. So wherever I see an x, I'm putting in a negative x and seeing what I have. So capital F at negative x is equal to negative 2x over absolute negative 1 times absolute x. Recall that if you have a product within an absolute value, you can split a product or a quotient within an absolute value, but not a sum or difference. So capital F at negative x is negative 2x over the absolute value of negative 1 is 1, and so we'll get over absolute x. So first conclusion, capital F at negative x is not equal to capital F at x. So F is not even. So do a little more work. Let's see what negative F at x is. So if I multiply both sides of our function by negative 1, we'll get negative sorry about that. We'll get the negative of this. So negative f at x is equal to negative 2x over absolute x. So we've got some success here, right? So we can say f at negative x is equal to negative f at x. So f is odd. And we're done. Okay, and finally, part C. Start out by plugging in negative x to our function and see if we get the original function back. So f at negative x is 2 times positive x to the fourth minus positive x squared, which is equal to f at x. So f at negative x equals f at x. So f is great, even. And we're good to go. Alrighty. So our next step is talking about intervals where a function is either increasing, decreasing, or constant. So a function f is increasing on an open interval I if for any choice of x1 and x2 in the interval I, with x1 being less than x2, we have the function evaluated at x1 is less than the function evaluated at x2. So basically, the y values are going up as we move from left to right for increasing intervals. Now, a function f is decreasing on an open interval I if for any choice of x1 and x2 in our interval I, with x1 being less than x2, we have our function values getting smaller. So as we move from left to right, the y values are getting smaller. A function f is constant on an open interval I if for all choices of x in the interval, the values of the function are equal. So all the y values are the same no matter what choice you make for the input value x. Okay, so something to keep in mind, we describe the behavior of a graph in terms of its x values. So when we're talking about intervals where something is increasing or decreasing, we're talking about x values. So let's just take a look at what's going on. So let's say we have, we'll just draw a picture. A few pictures here. Okay, so let's suppose that we had, I don't know, let's just say our x1 is here and our x2 is here. We can just pretty much do that the same on all these. It doesn't matter. They don't have to be the same, but. So now, what do you want to look at first? Why don't we look at the increasing function first? We'll just kind of go in order. So if let's just suppose that I have an endpoint here at x1, and my graph goes something like this, and it ends up at x2. Do you see that as I move from left to right and as I trace along this graph, do you see how the y values are going up? Here we have, this would be the function evaluated at x1, and over here would be the function evaluated at x2. So this is a picture of an increasing function, and the way we describe it, if you look at the values, the x values, this is the interval on which the function is increasing. So we would say f is increasing on x1 to x2. Okay, now let's take a look at a picture of a function that's decreasing. So let's have our endpoints be like this. And if we go something like that, we have our, as we move from left to right, but we trace along the graph, do you see that we're going down? All right, so that means that on this interval here from x1 to x2, right, those x values are, our function values are decreasing. So we can say on this one that f is decreasing on the interval from x1 to x2. Okay, so a constant function would have something going on like this. Let's say that we have this going on. You know, I meant this to be a horizontal line. I don't like that. Make this neater for you. Okay, so here, do you see we're neither increasing nor decreasing? We're constant. We have the same y value. So whatever this y value is, it's f at x1 is equal to f at x2, which is actually equal to all the x values on this interval from x1 to x2. So it would be here. So therefore, we would say f is constant on the interval from, good, x1 to x2. Actually, for this one, for all x, except we put endpoints on there. Okay, so let's let me write in. You know, I went up a little here. Let me redraw this so that It's truly decreasing because I had it kind of going up. Did you see that? So I don't want to do that. So this guy, call this one f at x1, and then down here we have our f at x2, which is a lower y value, smaller y value. And then here, again, we're talking about the interval on x, and so f is constant on that interval. All right, so now we get into local extrema. Local extrema. And if you take calculus with us, we use the Larson text, so they often call this relative extrema. So a function f has a local maximum at c if there is an open interval I containing this input c, that for all x in the interval, the function values are less than or equal to the function evaluated at that input c. We call f at c, so the y value is a local maximum value of f. Now a function f has a local minimum at c if there is an open interval I containing this input value c, so that for all x in I, f of x is greater than or equal to the function evaluated at c. So all the y values are above or equal to the function evaluated at this input value c. So we call f at c, in this case, would be a local minimum value of f. Okay, so the word local is meant to suggest that it is only near c. That is, in some open interval containing c, that the value of f at c has these properties. So when you say, you're local to North County, you don't mean that you're local to Chula Vista, right? You mean that you're local to maybe Oceanside or Del Mar or something like that. So local is near this domain value c. Now, the y value, f at c, is the local maximum or minimum value. It occurs at this x value c. So the wording can be a little on the confusing side. So let's just check out a little sketch and see. Okay, so let's say we have, some nice graph like this. Okay? So, stop me when you think that there would be a local max or min. Okay, ready? Okay, ready? Good, you got it. That right there would be a local maximum. So let's label this bad boy. So about right here we said, if we call this input value our first C1, we have this ordered pair C1, F at C1, right? So this is the, F at C1 is the Y value that corresponds. So there's a local good maximum at x equal to C1, and the local maximum is f at C1. Very good. Now, let's keep going. This is fun, right? All right, ready? Right again. So here we go. Do you see maybe about here? We have call this guy C2. So at this ordered pair, a local minimum occurs. A local minimum occurs. So that's a local minimum. So the local minimum is the function value. It occurs at C2. This guy is a local maximum. All right. And then ready? Oh, awesome. Here's our last guy. So this one, call it C3. And the function evaluated at C3 is another local, great, maximum. Okay, so far? Very good. So here's an example. So let's take a look at the graph of this function. So we're being asked, I'm sorry it's not super clear, but you can get the gist of it. We're being asked to find out on what interval or intervals is the function increasing. So take a look. The function value. Do you guys see that? Remember, as we're moving from left to right, when is this guy going up? Good. So if we start here and trace along, do you see on that interval, we've got an increase. Oops, sorry. I like doing the Y stuff in yellow. On this interval, we have an increasing behavior, but it's happening on the x values from 3 to 5. Does that make sense? So the intervals where this graph is increasing are from x is 3 to x is 5, and that's how you write it. Okay, how about decreasing behavior? So as the graph, we'll do decreasing in green, I guess. So as the graph is going, good, from left to right, do you see? Stops right there. And then again, it's going to behave, it's going to decrease over here. So the x values where that's happening, do you see, are going to be from minus infinity to I'm trying to figure out which colors I should use, because this is different stuff. I'm going to go ahead and I'll underline the X stuff. I think it's too confusing to use all these different colors. So this is what I'm going to do. So on the increasing stuff, I'll do the blue highlight because I have a corresponding pen I can use with that. So we've got for the x intervals, do you see it went from here to here? Now for the green, okay, it's going to go, this goes up. It doesn't have a stopping point. So basically, from here to here, do you see it's going to behave that way? So from minus infinity to minus 1, and then also from where to where? Good, from 5 to infinity. Those are the x values that correspond to the y values decreasing. So we would have, our answer would be from minus infinity to minus 1. You marry two intervals by doing this union business. And then we said it went from where to where? I think from 5, right, to infinity. Good so far? Okay, so that's our answer for part B. Okay, now on what interval or intervals is our function constant? Good, do you see? we have constant behavior right here, don't we? It's constant. And the x values where that's happening are here. So the answer for that one is going to be from, I think it went from -1, was it to 5 or to 3? -1 to 3 is where it changes. And if you wanted to, you can do the endings for these because we're not including right where the behavior changes. So this is the interval for the constant. This one is where the interval went, whoops, that's gray, for the decreasing here and here. And then for the increasing, we were from here to here. Isn't that cool? So you describe which intervals by describing the x values. Okay, so list the local minima. So here we go. There's actually, it's a little bit tricky, right? Do you see that there's infinitely many ordered pairs where the minima occur because they occur where it's constant, the local minima. So we're just going to list it. We have a local minimum, okay? And the local minimum occurs at when f, actually this was named y, so when y was equal to what? So what y value are we on at the constant function? Good, we're at -2. So when y equal -2 is the local minimum. We're not going to list the ordered pairs because we'd be here forever since there's infinitely many ordered pairs on that interval. Okay, now let's look at the relative maxima. So do you see? You can't count the arrows, right? Because they don't stop. They're going to go on in the behavior in that direction forever. But do you see here at 5, 2, the ordered pair 5, 2, we have a relative maximum. In that neighborhood, we have a maximum value of y equal 2. Okay, so we're just going to say for this one, there's infinitely many. This was that minimum one, ordered pairs. On x equal to -1 from x equal to 3. So list the local maxima we just said was at y equal to 5. So it's the y value. And the ordered pair, was it 5? No, it was y equals to 2. Let's look at it again. Yes, that's true. It's a y value of 2, and the x value where it happens is 5. So at y equal to 2. So the ordered pair where it occurs at 5, 2. Okay? All right. So absolute extrema. So if f is a function defined on this interval I, or n interval I, there's a number u, if there is a number u, in this interval for which f at x is less than or equal to f at u. Math people, they got to get their little FU's in there somewhere. For all x and I, then f at u is the absolute maximum of f on the interval, and we say the absolute maximum of f occurs at u. So u is an input value. Now, conversely, if there is a number v in the interval I, for which f at x is greater than or equal to f at v for all x and I, then f at v is the absolute minimum of f on I, and we say the absolute minimum of f occurs at v. So for our next example, find the absolute minimum and the absolute maximum, if they exist, of the following graphs. So let's check this one out. So on this, we have to look at this whole interval, and we're not considering local extrema. We just want the smallest and the largest y values. So do you see here, down here, this negative 145 represents the lowest y value? And what's the highest y value? Good. The highest y value is occurring at 44. So let's talk about what's going on. So there's I have some stuff written down here. Actually, I'll highlight it in different ones, different colors. So this is the highest one. So the absolute minimum is negative 145. Where does it occur? The absolute minimum occurs at negative 5. That's the x value where it happens. And the absolute maximum is, good, 44. And where did that occur? That one occurred at x equal to negative 2. Okay? All right. Next example. This one's a little tricky. Take a look at this one and tell me what you think. Okay, so here there's definitely an absolute minimum. But look at this problem child right here. Do you see, and we learned about this in calculus, do you see that this graph, as you go from left to right, there's a jump down here. This ordered pair, which is what, 3, 4, is not an ordered pair on the graph. The function evaluated at 3 is actually 3, this value here, because that's the ordered pair 3, 3. So basically, what's going to happen is we're not going to have an absolute maximum here, because we get closer and closer and closer and closer from either direction here. But we never quite attain this y value of 4. Okay, so let's jump down since we're talking about that. The absolute maximum is, it does not exist. There's no absolute maximum, and that's okay. All right. There's my kitty. I don't know if you can hear her. All right, but the absolute minimum, where's our lowest y value? Good. Do you see at y equal to 1? That's the lowest y value. And it occurs at x is 0. So the absolute minimum is 1, and it occurs at x is 0. Okay. So now the extreme value theorem states that if you have a continuous function whose domain is a closed interval, that means it includes the endpoints, then f, and continuous basically means that, at your level of math, continuous means that you can draw the graph without lifting your pencil. So there's no there's no vertical asymptotes or jumps or anything like that. So if you have a continuous function on this closed interval, then f has to have an absolute minimum and an absolute maximum. On the closed interval. So again, you can consider a continuous function to be a function whose graph has no gaps or holes and can be drawn without lifting the pencil from the paper. So if we had something like, I don't know, so this is a piecewise function. And do you see that I had to lift my pencil there? So that one has a discontinuity at this input value here, right? There's a discontinuity. So this function is not continuous. So if we did something over here, and basically, you know, if you can draw the graph without lifting your pencil, except of course at the end of the page, this one is an example of a continuous function. Okay. The average rate of change. If A and B, where A is not equal to B, are in the domain of some function y equals f at x, the average rate of change from A to B is defined as the average rate of change equals the change in y over the change in x, which is equivalent to the function evaluated at B minus the function evaluated at A all over B minus A, and of course A is not equal to B. And it's really cool because when you're in calculus, what happens is as B gets closer, A and B get closer and closer and closer together, what ends up happening is you can find the instantaneous rate of change. So kind of like when a policeman's using a radar gun, they're finding an instantaneous rate of change to figure out what your speed is, as opposed to figuring out overall what your rate was when you drove to Vegas. You know, you might be driving at many different speeds on the way. So there's some pretty cool stuff you can do. So let's find the average rate of change of this function at these different values. Okay. So first up, if we're going from 0 to 2, the change in y over the change in x, again, is the function evaluated at 2 minus the function evaluated at 0 all over 2 minus 0, because our a is 0 and our b is 2. So that will be equal to, so f at 2 will be negative 2 cubed plus 1. And then f at 0 will be negative 0 cubed plus 1 all over 2. So we will get, let's see, that'll be negative 8 plus 1, which is negative 7 minus 1 over 2. So we will have negative 8 over 2, which is negative 4. So our average rate of change of this function as x goes from 0 to 2 is negative 4. Now going from 1 to 3, change in y over change in x is f at 3 minus f at 1 over 3 minus 1. This will be negative 3 cubed plus 1 minus negative 1 cubed plus 1 all over 2, which will be, let's see, the first brackets are going to be negative 27 plus 1, which gives us negative 26, and then minus negative 1 plus 1, which is 0, all over 2. So that'll give us negative 13. Are we doing okay so far? Awesome. Okay, now from negative 1 to 1. So again, change in y over change in x is f at 1 minus f at negative 1 over 1 minus negative 1. Be careful with your signs. This will be negative 1 cubed plus 1 minus negative 1 cubed plus 1 all over 2. So we'll have, I think this first bracket will be 0 minus negative 1 cubed is negative 1. When you flip the sign on that, you get positive 1. So we'll have minus 2 over 2. So we'll get negative 1. Okay. So now it turns out that this extends to the slope of the secant line. The average rate of change of a function from a to b equals the slope of the secant line containing the 2 points a f at a and b f at b on its graph. So the secant line cuts the curve. So here, if we take a look, sorry, this is really zoomed. Let's zoom out a little. So h at x equal to negative 2x squared plus x. And we want to find an equation of the secant line containing the x coordinates from 0 to 3. So let's see. We've got, let's take a look at what the graph would look like for the original graph so we can get a picture of what's going on. So h at x is equal to negative 2x squared plus x. So why don't we find out what the y values are for these x coordinates that we have to find? So h at 0 is negative 2 times 0 squared plus 0. So h at 0 is 0. So that means the ordered pair 0, 0 is on the graph of h. And h at 3 will be negative 2 times 3 squared plus 3. So h at 3 will be, let's see, negative 18 plus 3, which is negative 15. So that means the ordered pair, good. 3, negative 15 is on the graph of h. So let's make a picture of h. So let's see, our x coordinates, why don't we have go from 5 to negative 5, because we're only going from 0 to 3 on there. And then how about for our function values for h, we'll go negative 20 to 20. So each of these tick marks will be worth 2. So if I plot my ordered pairs 0, 0. We might want to get another ordered pair just to get a feel for the shape of the graph. So h at 1 will be negative 2 times 1 squared plus 1. So h at 1 will be, what, negative 1, I believe. So 1, negative 1 is on the graph. So if I plot 1 will be here, negative 1 will be here, and then I'll go ahead and plot 3. So 1, 2, 3, and then 2, 4, 6, 8, 10, 12, 14, negative 15. So this is 3, negative 15, and this here was 0, 0, the start of our interval. So let's make our picture here. It'll look something like this. Okay. Now, we're going to be looking for the equation of this secant line. So I'll do the secant line in green. And if you just draw the secant line, it's going to look like this. Whoops, little bit off. Okay, so we want to find the equation for this secant line. So we've already gotten a lot of the information. So the slope of the secant line is going to be equal to, our function is named h, so h at b minus h at a divided by b minus a. Well, we already got that information. A is 0. H at a is going to be h at 0, which we found was 0. B was equal to 3. H at 3, I'll be consistent here. H at B is equal to H at 3, which we found was negative 15 up there when we were doing our graph. So the slope of our secant line will be H at B, which was negative 15, minus H at A, which was 0, divided by B minus A. So the slope of our secant line is negative 15 over 3, which is negative 5. Okay, so far? Now, using the point-slope form of the line, we can say y minus y1 is the slope of our secant line times x minus x1. So one of our ordered pairs was 0, 0, so let's use that. Y minus 0 is negative 5 times x minus 0. So the equation of our secant line is y equals to negative 5 times x. So now let's check it out. See how well our graph went. So do you see that we'd have a slope of negative 5, so that means for every 5 we go down, we go to the right one. So this would be 2, 4, 5 to the right one. We're right on target. Okay? So our graph looks awesome. Okay? So this line is this green line here is the secant line. So this here is the secant line we were looking for. Containing x is 0 and x is 3. Okay? And that wraps it up for today. So don't forget to go and do some of the work on the problem sets to cement your new math knowledge. And have a fabulous day. Ciao.